Anyway, so okay, so let me see. So where were we? We were talking about okay, so in a fluid, let me try and remind myself about what happens in that case. Why is the continuity equation not enough, so to speak? Let me look.
Well, the continuity equation doesn't allow you to effectively doesn't allow any of the fluid variables to feed back into the velocity. The continuity equation is
I
really
see.
just
Just
the convection equation for mass.
right, right. Okay.
So you need the Cauchy momentum equation. You need to have non-trivial coupling between velocity and pressure and those kinds of things, which you don't get from the continuity equation.
So the continuity equation merely gives you the relationship between velocity field and pressure.
Density,
Density, yes.
mass
Right,
density.
right. Okay. What's the analog in the general relativity case of what's the analog of this in that case? So you're saying
Well, I mean, the field equations can be thought of as being continuity equations for the energy momentum tensor.
no, they can't. That's a separate piece, right? The divergence freedom of T mu nu is separate from the field equations, right?
Not if you make sufficient assumptions on what the sort of content of the universe is. You can couple both.
I thought it was a separate condition. I thought the divergenceless of T mu nu was independent of, I mean, you can couple it if you include, I mean, T mu nu, if it was all gravitational radiation, then it would all be the same thing.
Right.
It would all be. But you're saying, okay, you're saying that it is sufficient in general relativity that this statement that the Ricci tensor
Mhm.
is 0,
Right.
which you claim is equivalent to the conservation of area for the bundle of GD6.
Right.
In other words, there are tidal effects, but no sort of no, there's a quadrupole effect, but nothing less than that, so to speak.
Right.
Okay, so the naive thought might be, okay, so that's a statement about what quadrupole effect there can be, and you're claiming that, I'm still not completely getting this. You're claiming that a higher order correction would lead to what? I don't understand. I still don't understand. It's we've got one condition on the shape of the bundle of GD6. You're claiming that the higher order correction gives you an additional constraint on the cross section of GD6. Yes.
Mm-hmm.
And what do the initial value data for that look like? Because if there's initial value data which purely on the basis of the existing constraint implies a unique G mu nu up to gauge transformations,
right.
what good does it do? If you put an additional thing in there, how does that work?
Right. You would need to specify additional data on the Riemann tensor.
Okay, so what you are effectively saying, I think, is that the gauge degrees of freedom are not quite as free as you thought they were.
Mm-hmm. Well, they could. I mean, they might be, but they don't have to be.
No, you're saying that the evolution that in the usual formulation, all that matters is the area.
Mhm.
So there are different gauges effectively in which the shape can be different, blah, blah, blah. And those are all equivalent in the normal formulation. There's no choosing between them and no
Mhm.
measurement you can make that will distinguish them.
Right, but there might exist additional constraints on the geometry of the cross section
Right,
that
right.
are
But
still
that would
gauge
be
invariant.
really, I mean, I don't understand. If for all values of the gauge, oh, you're saying, I see what you're saying. You're saying
You
if
can
we look
have
at the
geometrical data that's still preserved independent of how you slice the causal graph. Geometrical data
right,
isn't just area.
right, but that's basically saying, let's pull that back to the physics.
Mhm.
Right now, we believe that our G mu nu is free. There's a large family of G mu nus connected by gauge transformations that are all equivalent.
Mhm.
What this has to be saying, I think, is that if we were to trace the evolution of that, okay, so normally we trace the evolution and it comes out and it's in that gauge and it does what it does. And obviously it depends on the gauge, but the only measurable quantities we claim are ones that do not depend on the gauge.
Right.
Okay, now what you're saying is, what are you saying here? You're saying, I mean, let me give an analogy. In in one of these discrete manifolds, in the limit, all the continuum properties should just hold.
Mhm.
As you pull back from the limit, all kinds of weird stuff is going to happen. All kinds of
Right.
lattice effects and so on are going to happen.
Mhm.
Okay, so in this case, you're saying that the invariance that different initial data can lead to different outcomes, that normally you would just say that different initial data related by gauge transformations. Well, I mean, let's be concrete. Let's start a geodesic bundle that's in the shape of a Q or something.
Mhm.
Okay. And normally the equations just say you preserve the area of that.
Right.
But it could be the case that, in fact, that geodesic bundle puts them in the shape of an R.
Mhm.
But normally you don't think that's measurable somehow.
Right.
But this is saying actually there is a way to measure it.
Mhm.
What is that way? I mean, what are you measuring normally in general relativity? What do you think you can measure?
What you're
Gauge
normally
independently.
measuring, yeah, the measurable quantities in a gauge independent sense are really just projections of the space-time Ricci tensor, I think.
That's what I think too.
When you do gravitational lensing or whatever, that's ultimately what you're measuring. And so what this is claiming is that that one can also take projections of other higher order contractions of the Riemann tensor and have those contractions can correspond to measurable quantities too, if projected in the right way.
Right. Not only measurable quantities, but quantities that whose evolution is somehow determined.
Yes, right.
Because you can make, so that means that different choices of gauge would lead to experimentally different consequences, I think.
Right.
So we should unpack what this really means. What do you think the analog of the Knudsen number or whatever it is? Because normally, well, okay, in the derivation of Navier-Stokes, there are many things. There's a subsonic thing with Mach number. There's the, density of the mean free path thing, and so on. The mean free path thing is much more like how close are you to the underlying, network structure.
Right. I think the mean free path, the analog of the mean free path here is exactly sort of a reciprocal of a network distance.
Right. Okay. One would suspect that an analog of the Mach number is something about the strength of the, strength of the gravity, so to speak.
Right.
And when there is very strong gravity, very tipped light cones, etc.,
mm-hmm.
I suspect that, that's very interesting. When you tip it enough, it's going to matter. The distance, it's going to be much more sensitive to the distance between nodes.
Mm-hmm.
Sort of analogous to what happens in fluid flow, where when the fluid is moving fast enough, so the difference is, the issue is, when the fluid is moving fast enough that it's close to the speed of the molecules,
mm-hmm.
then it matters that there are molecules there. What is the analog here? The analog here what does strong gravity look like?
I mean, densely connected subgraphs. One would presume.
I'm not sure that's the whole story. I think there may be a situation in which one is dealing with slices. It's like cleaving a crystal. There are angles at which you don't hit very many atoms.
Right.
So similarly here, I could imagine that you can get a situation where you're anyway, I'm sorry, coming back to this, I want to come back to so your basic claim is that in this limit, in this thing, see, what's bugging me is there's no parameter that, okay, in the case of the fluids, there's the size of the molecules compared to the macroscopic size. Same
mm-hmm.
thing here, okay?
Right.
There's another parameter which is the flow speed. What is that? All that weird background noise? It's driving me a little bit crazy.
Is that on my end?
I don't know. Sort of a moving around type noise. Well, who knows?
I don't know.
No, that's the noise. Okay, in any case.
I don't think that was me. Hope not. Yeah.
Well, okay. So you see why I'm pushing on this, because there's something fishy here.
Mm-hmm. Right. Right.
There's some parameter we're missing. There's some analog of Reynolds number or something, or Mach number. I mean, the Reynolds number.
Right. I mean, as a trivial level, which is probably not very helpful, the most direct analog of the macroscopic flow velocity would be the relativistic fall velocity, because that is the thing that appears in the flux for the continuity equation.
Sure.
But I'm not sure that helps.
I think that it's going to be the choice of gauge.
Mm-hmm.
And that what's going to happen is there are some kind of extreme choices of gauge. Now, this is where we're getting lots of background noise, so I don't know whatever's happening is oh, now it went away. Usually you have a perfect audio setup, Jonathan. Well, now you're
hang on, wait. Let me try and unplug my microphone, see if it's
okay.
Maybe that has done something.
Yes, that's much clearer.
Oh, really? Okay.
Yeah. Okay. Well, have a think about this. I think there's something funny going on here.
Right. It's a good thing that we don't know that dark matter is Lorentz invariant, because it looks like it might not be.
Well, that's an interesting thought. You know, there's another thing going on with us, which is the comparison between curvature and dimension.
Mm-hmm. Right. Which I've now written up a thing on, formalizing the idea a little bit more.
Oh, okay. Send it to me.
Sure. Well, I'll put it on the Dropbox. It's in the updated relativity and gravitation paper.
Okay. You see, that might be is there a parameter that governs whether you should be talking about dimension or should be talking about curvature? I don't know.
Right.
Because those are
right.
Look, the basic point is the appearance of general relativity is going to happen in a limit here. You know, when things are very granular, it's not going to be perfectly correct.
Mm-hmm.
One question is, what are the first order corrections? Another question is, see, let me give you an example. In a cellular automaton fluid, the viscosity is determined.
Right.
Okay? Even though in standard theories of molecular dynamics, the viscosity is still a free parameter up to a point.
Right.
Well, actually, no, that's not correct. The viscosity depends on temperature and number density and things like that. But in the cellular automaton fluid, it's actually determined.
Mm-hmm.
So in this model, things which are undetermined in general relativity could be determined.
Right. Right. Well, preferred gauge would be one example.
Yes, indeed. And as we were talking about yesterday, I mean, the rest frame of the cosmic microwave background is even a preferred frame.
Right. And that's not determined by GR.
Even though it does follow from the initial conditions of the universe, doesn't it?
Yes. But you require additional constraints on radiation content of the universe and things like that.
Right.
But
now, wait a minute. What's the rest frame of the cosmic graviton background?
I don't know. Would it be the same?
I think it's the same. And that doesn't have anything to do with radiation. Well, it has much less to do with radiation.
Right.
Even if it was a Max, this is the now we're practicing for your PhD, whatever. Do you know the answer to this? What the
Well, not really.
uh, okay, so but if you
Well,
can you have a universe which has no matter in it and has just gravitational radiation and has a I mean the Friedman Robertson Walker thing involves dust, which
yes. Yeah, I believe
mass
it's
without pressure.
right, right. But you can't have. I believe it's the case. You can't have a homogeneous isotropic metric for an expanding universe that doesn't make some kind of hypothesis on how the scale factor scales with time. And in order to do that, you basically have to have a mass content, I believe.
Well, the question is, do you have to have that because general relativity is underdetermined, or do you have to have that because the physics is different?
I'd always assumed you had to have it because general relativity is underdetermined. Because in effect, what you're doing, right? What you're doing in FLRW, obviously, is just you're taking the 10 independent components of the Einstein tensor, you're reducing them to 2, and then you have to make a hypothesis on the discretized geometry parameter, the curvature parameter kappa, and you have to make a hypothesis on the scale factor A, because those 2 components are still left undetermined, even though the other 8 have been removed.
And how do you validate your hypothesis? So your hypothesis is that, but those are the initial conditions for the universe, effectively.
Right. So GR doesn't dictate whether you have kappa -1, 0, or 1 universe, and it doesn't dictate whether A scales like t to the half, t to the 1, t squared, whatever.
What does? That second thing.
That's the mass content. Determines the second thing. And the former, we don't know.
Well, okay, so
inflation partially.
Well, you're saying which former thing, which part? You're saying that the value of kappa.
Yes. Because the idea behind the solution to the flatness problem is that you say, irrespective of which region of basically irrespective of the exterior curvature of the initial hypersurface, you're still going to end up with a value of kappa that's arbitrarily close to 0. And the point is we don't know what determines that initial extrinsic curvature.
Okay, so the claim would have to be here that in this model, more is determined than general relativity determines.
Right.
Well, that's interesting. I mean, that would be unsurprising that you could determine more. But I'm still a little concerned about this higher order correction piece. Why is there no expansion parameter for the higher order correction?
Well, the expansion parameter, the A in the FLRW metric will be contained within the Ricci tensor.
And what does that determine? That determines something to do with the strength of curvature, basically.
Yeah, right. So 1 over that is a strength of curvature. Right. The A is the thing that appears in RTT, RRR, R theta theta, R phi phi.
No, I understand, but in the solution, in the homogeneous universe solution, it's the thing that determines, in the ODE for the universe, so to speak.
Yes.
It's the parameter that appears there.
Yeah, it's the thing. Yes.
but the question is,
it's the thing that appears in front of the spatial line element in the space-time line element. Or scale factor squared.
right. But you're saying that is undetermined.
Mm-hmm. Right. You still need to have some kind of ODE or
initial condition.
Yeah, initial condition for A.
Well, we also need the field equations.
Right.
For what? For the gravitational field?
No, for the matter fields which produce density.
Yeah.
I
See,
mean,
I
there are
knew
two
Max was going to
equations.
wake up here since Max has been actually trying to figure out universes with these properties. Okay, all right, please continue.
There are two equations. I mean, in order to simulate inflation, there is Friedman equation, which comes directly from GR, and there is field equations, which are, come from the field Lagrangian.
Yes. Wouldn't it be sad if we disprove the hypotheses of your thesis before your thesis is ready?
Well, that's fine.
It's actually this general relativity thing isn't quite right. So anyway, no matter. Okay, but I understand, but how many? But do you understand what Jonathan has been doing, Max? Yes? I mean, he's got... Oh, I don't understand. I just don't understand. Okay. In the current setup with GR, the shape of the geodesic bundle is determined by the gauge.
Mm-hmm.
The only statement from the Einstein equations is that the area of the cross sections must be conserved.
Mm-hmm.
Okay. This is saying, actually, given a particular gauge, which determines the shape, I see. So if the gauge determines the shape, normally the Einstein equations would allow you to mix with wild abandon the shapes from different... This is saying with a particular gauge, it produces particular shapes. But there may be families of gauges that all produce some, where the, I don't know, the octupole moment or something is determined by, is fixed or something, or is determined by your equation.
Right. You can have non-trivial geometrical features that aren't the area that are nevertheless preserved between different gauges.
No, because what do you mean preserved? No, I don't understand that. I don't understand that. Nevertheless preserved, but there exists. Okay, so the unspoken statement is, with a gauge you can change that area, that shape arbitrarily. I don't know if that's actually true.
Right.
So that would be one question. Is that in fact true? That with a gauge you can get from anywhere to anywhere, because it could be that the general relativity thing is true, but there are additional constraints, because in fact whatever gauge you choose, that area can't be in the shape of an elephant or something.
Right. Well, that's exactly what I'm saying, that there are certain geometrical constraints that exist independent of gauge that aren't area.
I see what you're saying. Okay, so what you're saying is you can change around what you get for that cross section.
Mm-hmm.
But you can't change it arbitrarily. The initial data.
Right.
Okay. All right. So what? So, okay, so that means that there is an additional constraint, which means that the initial value, all of these theorems about initial value stuff would have to be changed.
Mm-hmm. Right.
So then it would become just true or not true that cosmic censorship, these things that can't be proved from the existing Einstein equations would probably immediately fall one way or the other.
Right. Yeah, I suspect strong cosmic censorship will end up being somewhat trivial in higher order theory.
Okay.
But
okay, so what measurable consequence? Okay, so the statement, so this would predict certain features of the universe that have been unpredictable by general relativity.
Right. Right.
Well, the main thing that's unpredictable by general relativity is features of matter.
Which would probably remain unpredictable.
But considering the dark matter problem, for example, right? Knowing Humph. I don't see how this would address that, because I don't know, are there relic field configurations from, this seems hard to believe. I mean, there are really bizarre possibilities, like, for example, every galaxy was seeded by an initial perturbation, and that perturbation is still sticking around. But I don't think that that's consistent with what one knows.
Right, right. I mean, I think the most plausible way that you could get something like a dark matter correction is, as I say, by the fact that this whole calculation is in some way length scale dependent. It's dependent on the analog of a mean free path.
But that's microscopic. That's incredibly tiny. So
right.
I don't see that. I think the more likely thing there is this interplay between dimension and, which we haven't really addressed. We don't know. Okay, the statement that we can get GR if there is an asymptotic dimensional whatever.
Yeah.
The next question is, what if it's only, okay, there's different expansion orders, right? So what we need is the analog of some kind of Reynolds number that is the trade-off between dimension and curvature.
Right, right.
Okay, so first statement is, it might be the case, it probably is the case in this model, that this model determines more than general relativity determines. That seems unsurprising. Okay, so the next question is trade-off between curvature and dimension. I mean, and this is the n of r function, n sub r function.
Right.
And the question is, what parameter it's kind of the difference between a power law n sub r and a polynomial n sub r.
Right.
I think. So for small r, you can already tell the difference. I mean, between actually, I don't know to what extent. I mean, we looked at that. I mean, you can.
Right. It's visible for small r and for large r, but not for kind of intermediate r.
What's not visible for intermediate r? The difference between r to the d and what do you mean?
The trade-off between dimension and curvature.
Well, you're saying for small r, you can just count the nodes and you can plainly tell.
Right. And for large r, you'll get you'll be bitten by the fact that power laws beat polynomials. And so it's only there's a sort of intermediate range of r's for which the two become hard to distinguish.
So Imagine a version of Einstein's equations where dimension changes with time.
Right.
Where you don't have an asymptotically constant dimension. Okay.
Well, hang on. Those statements aren't equivalent.
No, they aren't equivalent.
Right. You can have asymptotic dimensionality preservation and not have constant dimension.
All right, but the question is, in your limiting process, is there an alternate solution in which the dimension changes?
Do you mean changes whilst still not limiting to a fixed value?
Oh, I don't know. It could limit to a fixed value, maybe.
Oh yeah, I mean that's absolutely fine. In fact, you want that to be true for cosmology.
Yeah, but can you write down the analog of the Einstein equations for the case where the dimension changes?
Yes, because they're the same. Because what happens is the Einstein equations, they're equations not on the hypergraph but on the causal graph. So if the dimensionality changes over time, when you take the continuum limit of the entire causal graph, you still have effectively a fixed dimensionality at the end.
No, because different slices of the causal graph can have different effective dimension.
Yes.
Okay, listen. Anyway, yeah, go ahead. I'm just
But the point is that what you're making is a limiting statement. As long as the thing limits to a fixed number of dimensions, it doesn't matter. You still get the Einstein equations.
Yeah. I'm trying to understand what the kind of measurable consequence of the whole thing actually is.
Mm-hmm.
I think we're getting closer. We're not there yet. Okay, should we look at this meshing thing, or we could do that a little later, or how do you guys want to do it? I mean, I'm really keen to try and finish this section, but we could look at this for a little while now if you want to.
Sure. I have to disappear for about half an hour soonish, but then I can be back later if we want to do meshing.
Why don't we do that? Why don't I work on what I was working on, and then I'll be in a much more patient state. And then Max, if you're
I can fix a random Wolfram model.
That would be good. And then, yeah, take care of some of these immediate things, and then we will reconnect later. And we're going to look at geodesics on meshes. I'd like to talk about another thing, which is rules that preserve planarity. Whether we have any hope of being able to figure out which of these do that.
The minimal particle case.
Yeah.
Well, you should be able to construct them pretty easily.
What's a test for whether they preserve planarity? How can we run a test?
Well, we can test if they don't preserve planarity very easily by running it. Well, I mean, it's not guaranteed, of course, but
well, wait a minute. What we could do is we could start with a bunch of planar graphs and see whether it keeps them planar.
oh, that's a bit more tricky because I have to have the structure which this rule would even do something with.
Well, so what? I mean, you just enumerate graphs and it's actually not a bad idea. We just enumerate planar graphs and we see which rules do something that preserves that planarity.
Isn't it just a question of computing subdivisions of the right-hand side and seeing if we get any that are isomorphic to K5 or K33?
The right-hand side of the rule.
Right.
I think that's completely unobvious when it picks up more than one edge on the left-hand side.
Well, that's why we'd compute subdivisions.
Of the rule?
Of the graph in the right-hand side of the rule. Because if there's a non-trivial knitting of edges that produces a subgraph that's isomorphic to K5 or K33, that will then appear as a subdivision. I think there should be a combinatorial way to do this.
From the rule. Give it a try.
Yeah, I think so. I don't know. Yeah, I can mess around with it.
You know, Jonathan, I have to say, in your stack of random pieces of expertise, the fact that you happen to have also worked on graph theory is really very entertaining.
Yeah, it's good. I'm enjoying this.
Right, you've got 3 hits: general relativity, automated theorem proving, and graph theory.
Yes.
That's surprising. Anyway, okay.
Sean, I don't think right-hand side is enough, because if you can imagine, wait a second. I need to think about it more.
No, I mean, I agree that there's obviously this issue.
But it seems deleting stuff is also important.
Yeah, right. But so I think you'd have to compute subdivisions and graph minors or something, and even then it would be a necessary condition, but it might not be a sufficient one.
Do we have something that generates planar graphs? Do we have a planar graph generator? Do we have can somebody find a list of planar graphs?
Yeah, there'll be we have a planar graph function.
I know. What do you mean? Yeah, no, I know that, but but it doesn't do what I want is an enumeration of planar graphs. I think in graph data we probably have a bunch of planar graphs, but I would like to get
Well, we can enumerate hypergraphs and then test if they're planar, but that might be slow.
What on earth is the analog of planarity for a hypergraph?
Well, we turn hypergraph into normal graph in one way or another, and we test if it's planar or not. We can just turn each hyperedge into a sequence of 2 edges.
I'm going to start with ordinary graphs, see what we get. All right, okay.
So, but we can enumerate ordinary graphs with hypergraph enumerator. Unless we have a better way of doing it.
That's incredibly brain dead that there are graphs which have.
Wouldn't the natural, I'm trying to think, wouldn't the natural generalization of planarity for a hypergraph be that you can lay it out you can lay the thing out on a plane where the vertices are boundaries of of faces in such a way that those faces don't intersect?
Probably.
Well, yeah, one way, I guess, to do it would be if you have 3 edges, we can look at it in 3D and check if these polygons between them don't intersect.
Right, exactly. So yeah, so in the 3-edge case, it would be can you lay it out on the plane as a tessellation of triangles?
On a plane or in 3D? Such that polygons for each hyperedge don't intersect in 3D.
Yeah, okay. Yeah, I see what you're saying.
I think it'd be interesting. Let's just see. It doesn't look like an NKS. I have some lists of planar graphs, but I don't seem to have a big thing there. Um, there seems to be a thing called House of Graphs on the web. Well, that's nice. I wonder if it actually has the graphs. Let's see if this just works. Ta-da! That's cool. Look at that. Just worked.
What is that?
What?
What is that?
What is it?
What,
It's a
yeah,
list
what
of
is this
plain...
file format?
Oh, it's a graph file format. You want to look it up and see whether it's usable for hypergraphs?
For sure. I mean, it seems really short given how many graphs it has. How they will fit in there.
I think it's binary format. I mean, actually, let's look up how it works. I think there's a new version of it that somebody was just mentioning. Yeah, why don't you look it up? Because that actually seems like it might be interesting to us. Anyway, this seems very useful because this means we can now evolve every one of these from and see whether it retains polarity. I mean, presumably if we now say, now these are undirected graphs and we will need directed graphs. So we will have to take these and, you know, put directions on them, right? I mean, each graph, there's many ways to put directions on it.
Yeah. Well, apparently G6 format doesn't support multiple edges.
Oh. Okay. I think there's a newer format that maybe is better. Okay, anyway. Okay, let us reconvene later. Let me work on my stuff here. Okay, so
Well, actually, maybe there are multiple variations, so it looks like some of them do support multiple edges.
well, figure out what's interesting. Okay, I'm going to disappear here. To be continued, guys. Okay.
Talk to you soon.
Can you give an estimate of when we'll be back?
Like 2 or 3 hours.
Okay.
Okay. All right.
See you then.
See you soon. Okay. Bye-bye. Bye.
See you.